Okay, let's have a look at lesson 2 of chapter 2. Today we're going to have a look at derivative rules part 2, which is about more complex derivative rules. So first of all, let's have a look at today's learning goals. After this lesson, you are expected to be able to understand the chain rule for differentiation, apply the chain rule for differentiation to solve related problems, understand the implicit differentiation method, and apply the implicit differentiation method to solve related problems. Okay, before we proceed to today's lesson, first let's give it a quick recap of the rules we have already learned regarding the derivative of a function. So first of all, we have learned the derivative of a constant function, which means the derivative of a constant function is 0. Next, the derivative of a power function, fx equals x to the power of n, where n is any real number. The derivative of this function is n times x to the power of n minus 1. Then the constant multiple rule states that if fx equals a constant c times a function gx, then the derivative of fx equals c times the derivative of the gx. Next is called the sum rule, which means if fx and gx are both differentiable functions, and the new function rx equals sum of these two functions, then we have the following relationship. The derivative of rx equals the derivative of fx plus the derivative of gx. And similarly, we have the difference rule. If gx and fx are both differentiable functions, hx equals the difference between fx and gx. Then the derivative of hx equals the difference between the derivative of fx minus the derivative of gx. Of course, you can also denote that using the Leibniz notation, right? Next, we have learned the product rule. If px is fx times gx, then the derivative of px is the derivative of fx times gx plus fx times derivative of gx. Then the quotient rule. If qx equals fx over gx, then the derivative of qx is a ratio between two expressions. The numerator is f, the derivative of fx, times gx minus fx times the derivative of gx. The denominator is gx squared. Of course, gx cannot be 0, right? Okay. Today, let's have a look at a new rule to evaluate the derivative of a given function. This is called a chain rule. So the chain rule states that if g is differentiable at x and f is differentiable at gx, then the composite function h equals f of g of x is differentiable at x, and the derivative of hx is given by the following expression. The derivative of hx, h prime x, is the derivative of f with respect to gx. So that's the derivative of the exterior function times the derivative of gx with respect to x. That means the derivative of the interior function gx with respect to x. The chain rule has a particularly simple expression if we use the Leibniz notation for the derivative. The quantity, the prime of f with respect to gx, is the derivative of fx, is the derivative of x with x replaced by g. This can be written as df by dg. As usual, the derivative of gx equals dg by dx. Then we can use the Leibniz notation to express the chain rule as df by dx equals df by dg. That means the derivative of f with respect to g, right? Which means the derivative of the exterior function times the derivative of g with respect to x, which is the derivative of the interior function. So note here that dg by dx is not a fraction, that is not literal division, but a single symbol that means the derivative of gx with respect to x. Nevertheless, it turns out that what looks like trivial arithmetic and is therefore easy to remember is really true. Okay, so this is a concept of the chain rule, which is a little abstract. So we'll not cover the proof of the chain rule. If you are interested, we can discuss the proof after this class. Okay, because it involves a more rigorous definition of the derivative, which is not covered in this course. Okay, so I'll give you 3 minutes to have a look at the chain rule here. Probably want to write this down on your notebook. And then we'll use the chain rule to solve some of the following questions. Okay, I'll show you some examples of how we can apply the chain rule. Okay, have you finished? Now, before we proceed to the next exercise, let's correct a little typo here. So actually, this should be gx cannot be 0, not the derivative of g. Let's correct this. Okay, next let's have a look at a example. So here we are given two expressions of two functions. Can you differentiate each function using the chain rule? Okay, I'll show you how we can do the first one and leave the second one to you by yourself. Okay. Right, for the first question, so we can treat the exterior function is something to the power of 4, right? So let's say we can treat this function is a composite function. So fx equals u to the power of 4, right? Where u is 3x minus 5. So that is really a composite function. F is a function of u, then u is a function of x, right? Therefore, according to the chain rule, we have df by dx is actually df by du, because f is a function of u, right? Times du by dx, because u is a function of x. So let's consider what is df by du. df by du is a derivative of fx with respect to u. Therefore, that is actually 4 times u to the power of 3. Then times du by dx. So that's the derivative of u with respect to x, which gives us 3. Because the derivative of this function with respect to x is 3, right? So that is really 4 times. So what is u here? U is 3x minus 5. So that's 3x minus 5 to the power of 3 times 3. So this is 12 times 3x minus 5 cubed. So this is the derivative of fx with respect to x. So if you are very familiar with the chain rule, you can also express that without explicitly state the u here. So you can treat this is a composite function, right? So fx with the derivative of fx with respect to fx is the derivative of the exterior function, which means something to the power of 4. So first of all, we find the derivative of something to the power of 4. So that's basically 4 times 3x minus 5 to the power of 3. Then times the derivative of the interior function with respect to x, which means 3x minus 5. The derivative of this function with respect to x, which gives us 3, right? So if you are very familiar with the chain rule now, you can also directly express the derivative of fx with respect to x as this. You don't have to explicitly use the notation u here. You understand? Okay, so I'll give you 3 minutes to have a look at the second question. If fx equals the square root of 4 minus x squared, what is the derivative of fx? Okay, have you finished? Okay, let's try to write the derivative of fx with respect to x here. So here, note we can treat this function as u equals 4 minus u x squared, right? So the outer function is fx equals square root of u, right? Inner function is u equals 4 minus x squared. So the derivative of fx equals, first of all, df by du, right? Which means the derivative of this function, which is 1/2 times u to the power of -1/2. So u is 4 minus x squared, right? So that's 4 minus x squared to the power of -1/2. Then times the inner function's derivative, which is 4 minus x squared, the derivative 4 minus x squared with respect to x. So that'll give us 0 minus 2x, right? After simplification, that'll give us negative x times 4 minus x squared to the power of -1/2. Well, you can also express it like negative x over square root of 1 minus x squared. Well, that's the derivative of fx with respect to x, according to the chain rule. So basically, the chain rule is applied when you want to evaluate the derivative of a composite function. Any questions? Any questions? No? Okay, so let's have a look at another example. Apply the chain rules this time. Use Lebanese notation. Okay, first, a function is y equals negative square root of 4x squared minus 3x squared plus 1. Second question, y equals 2x minus x. Sorry, I think there is a typo here. This should be 2x minus x cubed to the power of -3. Okay, I'll give you 5 minutes to think about these two questions here. Okay. Okay, have we finished? Let's have a look at the solution. Well, first question is here. And this is the second question. So now let's have a look at the solution of these two questions. First of all, question A, y is actually a composite function. Y can be expressed as negative square root of u. Then u is 4x cubed minus 3x squared plus 1, right? Therefore, according to chain rule, dy by dx is dy by du times du by dx, right? So dy by du, so note here, if you treat u as independent variable, dy by du is actually -1/2 times u to the -1/2. Then du by dx is this function, the derivative of this function with respect to x is 12x squared minus 6x, right? Then you can replace u as the expression in terms of x. So that is -1/2 times 4x cubed minus 3x squared plus 1 to the power of -1/2. Then times 12x squared minus 6x. Then after simplification, the final result is -12x squared plus 6x divided by 2 times square root of 4x cubed minus 3x squared plus 1. You understand? Do you have any questions? Okay, if no questions, let's have a look at the second one. Second one, y equals something negative to the power of -3, right? So the outer function is something to the power of -3. The inner function is 2x minus x cubed. So we can let y equals u to the -3. Then the derivative of the outer function is dy by du, which is -3 to the power -3u to the power of -4. The inner function is u equals 2x minus x cubed. The derivative of the inner function, du by dx, is 2 minus 3x squared. Then dy by dx, according to the chain rule, is the derivative of the y with respect to u times the derivative of u with respect to x. Then dy by du is this expression. Du by dx is this expression. Then we can plug them there. The final result is -3 times 2 minus 3x squared over u to the power 4. Of course, you can also express that to 2x minus x cubed to the power of 4, right? So when x equals 2, you can plug x equals 2 to that expression, then evaluate dy by dx at x equals 2 is actually 15 over 1 to 8. Okay, so I'll give you 3 minutes to have a look at the solution here. Any questions, just let me know, okay? All right, if you finish, let's see another example. Determine the equation of the tangent to fx here at x equals 0.5. Write the equation of this tangent line in the slope-intercept form, okay? I'll give you 5 minutes to think about this question by yourself. So note here, this function is also the later part of the function is also a converted function, right? So be careful with that. Okay, have you finished? Let's have a look at the solutions here. Okay, first of all, we find the slope of the tangent line to x at any point. So that's the derivative of fx at any point x, right? So according to the product rule, the derivative of fx equals, we can treat this is the first function and this is the second function, right? The derivative of the first function times the second function plus the first function times the derivative of the second function. Then the derivative of 3x is 3, then times 1 minus x to the power of 2. Then 3x times the derivative of the second function. So note here, the derivative of this function is actually a derivative of a composite function, right? If y equals 1 minus x squared, this is actually y equals u squared and u is 1 minus x. So the derivative of y in terms of x, dy by dx, is actually dy by du times du by dx, right? So first of all, the derivative of y in terms of u with respect to u is 2u. Then times du by dx is -1. So that's really 2 times x minus 1 times -1. Understand? And of course, if you are familiar with this already, you can directly write the derivative of this function here, which is 2 times the outer function to the power of 1. Then times the derivative of the inner function, which is 1 minus x, which is 1 minus 1, right? So the first part is 3 times 1 minus 2x minus 1 minus 2x plus x to the power of 2. The second part is 3x times 2 minus 2x times -1. Then expand and simplify. The final result of the derivative of fx with respect to x is 9x squared minus 12x plus 3. Then we know that the slope of a tangent line to fx at x equals 0.5 is just insert 0.5 to the derivative of fx. Then we get the slope of a tangent at x equals 0.5 is negative 0.75. Then we evaluate when x equals 0.5, the value of this function fx equals 0.375. Then we know the point slope form of the tangent line at x equals 0.5 is y minus 0.375 equals negative 0.75 times x minus 0.5. Because simply we know this line, the slope of this line is 0.75. And this line also passes through this point, 0.5, 0.375, right? So we can express that line use a point slope form, which can be converted to the slope intercept form, which is y equals negative 0.75x plus 0.75. Any questions? Okay, so I'll give you 3 minutes to have a look at the solution here. Any questions, just let me know, okay? Okay, if you have no questions, let's have a look at another example. Apply the chain rule to solve a rate of change problem. So Andrew and David, two persons, both leave their houses at 7 a.m. for their Sunday run. Andrew's house is 22 kilometers south of David's house. Andrew runs north at 9 kilometers per hour, while David runs west at 7 kilometers per hour. Determine the rate of change of the distance between the two runners after 1 hour. So this is a real world problem. So in order to solve this question, first of all, probably you want to draw a diagram to illustrate this problem first, okay? Try to model that problem based on your diagram, and probably that involves to calculate the derivative of any functions because it asks you to determine the rate of change, right? Rate of change at some specific time. Okay, first of all, try to draw a diagram to illustrate this problem. Okay, I'll give you 5 minutes to think about this question here. Okay, have you finished? Let's have a look at the solution. Okay, we can draw a diagram to illustrate this question like this. So David's house is at the north point, right? Andrew's house is at the south end. So now, actually, we need to study the case where 22 minus 90 that is greater than or equal to 0. That is when t is smaller than or equal to 29 over 9, 22 over 9, right? Because we know the total length is 22 from David's house to Andrew's house. Okay, so distance between the two runners, ST, is obtained by using two formulas, D equals VT and Pythagorean theorem. Andrew runs at 9 kilometers per hour, so the distance he runs is 90, which is here, with T measured in hours. Since his house is 22 kilometers from David's, the distance he is from David's house as he runs is represented by 22 minus 90, which is this side, right? Davis runs at 7 kilometers per hour, so the distance he runs is represented by 70 here. Then we know ST, the distance between the two runners, according to the Pythagorean theorem, is square root of 29 minus 90 square plus 70 square, which can be simplified to this expression here. Then we can find the derivative of ST. So note here, this is a composite function, right? So actually ST equals u to the power of 1 over 2, and u equals 130t squared minus 396t plus 484, right? This is a composite function. So according to the chain rule, the derivative of ST equals the derivative of the outer function, which is 1/2 of the long expression here to the power of -1 over 2, times the derivative of the inner function with respect to t, which is the derivative of this function with respect to t. After simplification, this gives us the derivative of s with respect to t is this expression here. Then we want to find the instantaneous rate of change when t equals 1. So we can insert t equals 1 to this expression and find that the instantaneous rate of change at t equals 1 is approximately -4.6. So that means after 1 hour, the distance between Andrew and David is decreasing at 4.6 kilometers per hour. Any questions? Okay, I'll give you 2 minutes to have a look at this solution here. Okay, any questions, just let me know. All right, if you don't have any questions, let's have a look at the next key point of today's class, which is about another important method we can use to find the derivative of a function, which is called the implicit differentiation method. The implicit differentiation method is helpful when differentiate an explicit function or multi-value function. Okay, so first of all, let's have a look at an example of the explicit function here. So for example, if we have a function like y equals 3x plus 5, or y equals x squared plus 6x minus 8, if you want to find the derivative of y with respect to x, in this case, we can directly find the derivative of y with respect to x is 3 for the first function, right? For the second function, because the expression of this function is explicit, then the derivative of y is just the derivative of this expression here, right? So that's 2x plus 6. Well, in the implicit function examples, we say that the expression of y with respect in terms of x is not explicitly given. For example, if we are given only x squared plus y squared equals 25, it is not given in the y equals something x, is not in this form, right? Therefore, we say the expression of this function is not explicitly given. Or in the second case, if we have the relationship 3x squared minus 5y squared plus 9x equals 25 minus 15y. Again, the expression of y with respect to x is not explicitly given in this form, right? Y equals fx. The expression of fx is not explicitly given. In this case, rigorously speaking, these are multi-value functions because for any given x, for example, x equals 2, there might be more than one y values corresponds to the given x input. However, they are still differentiable at some points. The problem is that how do we differentiate the expressions on the right side more quickly? Of course, you can solve y equals fx. Find the explicit expression of fx first, right? For example, in this case, in the first case, y squared equals 25 minus x squared. Then y equals either positive or negative 25 minus x squared, right? Then you can find the derivative of y with respect to x. But in the second example, it's more difficult to find the explicit expression of fx, right? So the problem is that how to differentiate the expressions like the ones on the right side more quickly. Then we can use actually the implicit differentiation method. Okay, so next let's have a look at the method in detail. In implicit differentiation, we differentiate each side of an equation with two variables, usually x and y, by treating one of the variables as a function of the other. Then this calls for using the chain rule. For example, in this function, in this multi-value function, x squared plus y squared equals 1. Here we can treat y as a implicit function of x, right? Then actually we can differentiate both sides with respect to x. So that means for the left side, we differentiate x squared plus y squared with respect to x. So that's dx squared plus y squared by dx equals the right side, also differentiate d1 by dx. So for the left side, remember y is a function of x, right? So according to sum rule, we have dx squared by dx plus dy squared by dx equals the right side. Right side is just a different derivative of a constant, which is 0. Then for the left side, dx squared by dx is just 2x, right? So you need to pay attention here. What is dy squared by dx? So first of all, this is a composite function, right? The outer function is u squared, and inner function is u equals y, which is actually a function of x, right? So we need to use the chain rule. First of all, dy squared by dx is the derivative of the outer function, which is the derivative of y squared with respect to y, which is 2y. Then times the derivative of the inner function, which is the derivative of y with respect to x. So that is dy by dx. Then this gives us 2y times dy by dx equals negative 2x. Then dy by dx equals negative x over y. That means the derivative of this function, the derivative of y with respect to x, is related to both x and y, not the x itself. So notice that the derivative of y squared is 2y times dy by dx and not simply 2y, okay? So in the explicit differentiation method, usually we'll use the chain rule. This is because we treat y as a function of x. Okay, I'll show you an example to illustrate this method in detail. So let's consider this example here. Can you find the slope of the tangent line at the point 1, 2 to the graph of this function here? Okay, if you want to find the slope of the tangent line, actually we want to find the derivative of this function dy by dx, right? So note here, this is an implicit expression of this function because we don't know y equals fx. We don't know the expression of fx explicitly. Therefore, we can differentiate both sides in terms of x. Then we have dx squared by dx. Second part is plus dxy by dx plus the third part, dy squared by dx. Equals the right side. Differentiate derivative of the right side is just a the constant derivative. Then this gives us okay, first, the derivative of x squared with respect to x is 2x, right? Second part is this is a product of two functions. The derivative of a product of two functions equals the derivative of the first function, which is x, with respect to x, times the derivative times the second function, then plus the first function times the derivative of the second function with respect to x. So that's dy by dx, right? Then plus the derivative of the third function with respect to x. So remember, y is a function of x, so this is a composite function. To evaluate the derivative of a composite function, we need to use the chain rule here. So that equals the derivative of the outer function, which is y squared with respect to y. So that is 2 times y. Then times the derivative of the inner function, which is dy by dx, right? Which equals 0. And this gives us 2x plus dx by dx is of course 1, right? So that's y plus x times dy by dx, then plus 2y times dy by dx, which is 0, right? Then let's combine all the similar terms. So 2y plus 2x plus y plus x plus 2y times dy by dx. Remember, we want to solve dy by dx, right? So we can move 2x plus y to the other side. Therefore, we have dy by dx equals negative 2x minus y over x plus 2y. Of course, for x plus 2y is not 0. Okay, this is a limitation for our variables. Therefore, we can evaluate the slope of the tangent line at this point. So when x equals 1, y equals 2, we will have dy by dx equals negative 2 minus 2 over 1 plus 4, which gives us negative 4 over 5. Understand? Okay, any questions here? Okay, so let's have a look at the solution in a formal writing here. So actually, if you draw the graph, if you sketch a graph of this function, you can see actually this is the graph of this function is actually an oval like this. So at the point 1, 2, it's probably here. The slope of this line is a negative number minus 4 over 5, like this. Okay, have a look at this question. Any problems, just let me know, okay? This is tangent line at this point. 1, 2.
老师，那个
Okay, let's make summary of today's lesson. So today we have learned 2 more derivative rules, right? First of all, you should be able to understand the chain rule for differentiation and apply the chain rule for differentiation to solve related problems. Next, you should also be able to understand the implicit differentiation method, and then apply the implicit differentiation method to solve related problems. So note here, usually in implicit differentiation method, be careful with the expression like y squared or xy. In order to evaluate using the implicit differentiation method, usually you should also use the chain rule to evaluate some of the derivatives, okay? Okay, so basically, so far we have learned these rules to evaluate the derivatives, right? And after today's lesson, you should update your list, adding the chain rule and the implicit differentiation method. Okay. Update your list of the common rules plus a chain rule and implicit differentiation method. You can use this method to find the derivative of a function. Okay, so that's the end of today's class.